I've got an equation for another surface up here. I could view what I have on the left-hand side here as some function of three variables, and this would just be the level surface, all of the points in the domain that would map to a W value of 5. I can also just view this as an equation in three variables, whose graph would be some surface in free space. That surface may or may not pass the vertical line test. My guess is it doesn't. My guess is that this is not a single function. I don't see a nice way of solving for z. But I can say that sections of that surface that do pass the vertical line test are functions where z is a function of x and y, and the formulas for all of those functions, for all of the pieces of the surface that pass the vertical line test, are encoded in this equation. So we should be able to then find our partial derivatives. So I should be able to find a formula for the partial of z with respect to x and for the partial of z with respect to y. Okay. Now, in the last example we did, we had a much simpler equation. It was just x squared plus y squared plus z squared. So the three variables that were playing three very different roles were in separate terms, and that made things a little bit easier. Okay. So what I'm going to suggest is that you pause the video and try to work this out. Try to find both partials for me, okay, and then tune back in and we'll work through it together. Welcome back. Okay, if I'm finding the partial of z with respect to x, I find it helpful to just label what my three variables are. And it's going to be different when I find the partial with respect to y. So I'm just doing the first part right now. Okay, so x is going to be my input variable or my independent variable. Y is going to be constant, and z is some function of x and y. And we just haven't bothered to solve for z, so we haven't found an explicit formula for it. I find it helpful to just go through and put parentheses around my z's. Not absolutely necessary to do that, but that just sort of tells me, okay, that's a separate function of x and y. All right, I'm already kind of used to thinking of one variable as constant. That reminds me, oh, in addition to that, one variable is a function of the other two. All right, so if I take the partial with respect to x of both sides, and I'm going to go through and just again mark off that z is a function of x and y. Okay. Again, if we want to boost our confidence, we can start with the right-hand side. That's going to be 0. Okay, for this first term, we've got an exponential, so we're going to get e to the xyz. And then I've got to multiply that by the derivative of xyz. But for that, I'm going to need to use product rule, because that's a function of x and y, and that's a function of x and y. Okay. So the partial of x times y, since we're treating y as a constant, that's just going to be y times the other function, z, plus this first function is x times y times the partial of z with respect to x. Okay. All right, plus, now derivative of sine is cosine, so we'll get cosine of xz. And then I've got to multiply by the derivative of x times z. That's another product rule. Okay. So the derivative of x is just 1 times z plus x times the partial of z with respect to x. Okay. And then minus, now here this piece is actually a lot nicer because y is just a constant, so I'm going to get that constant times the partial of z squared. Now that's going to be a chain rule. So I'm going to get my y times the derivative of the squaring function is going to give me a 2z, and I'm just going to write the 2 in front, times the derivative of the inside part is the partial of z with respect to x. One thing that can be helpful as you're doing this, if I just go through and I count, I had z 1, 2, 3 different times. Before I do any simplification, once I'm just done taking the partial derivatives, I should have written the partial of z with respect to x the same number of times. And it looks like I have. I've written it 3 times. Okay, so now I want to solve for it. So let's see, we had it here, here, and here. Looks like the first thing I'm going to want to do is do some distributing so that I can break these two out of their brackets. So we're going to have yz times e to the xyz plus xy e to the xyz times the partial of z with respect to x. My convention is usually I'll bump things to the front if there's any chance of me thinking it's in the exponent position, but I'm always going to write the del z del x at the very end. Not absolutely necessary, it's just that's where I look for it. It's at the end of my terms. Okay. So here, this would become plus z cosine of xz plus x cosine of xz times the partial of z with respect to x, and then minus 2yz times the partial of z with respect to x. And that's all equal to 0. Okay. So at this point, this term and this term and this term have a partial of z with respect to x in them. I'm going to keep them on the left side and move everything else over to the right side. Okay, so staying on the left, we've got xy e to the xyz times the partial of z with respect to x plus x cosine of xz times the partial of z with respect to x minus 2yz times the partial of z with respect to x. And that's going to equal, I'm subtracting everything else over, so I'm going to get a minus yz e to the xyz. I'm going to get a minus z cosine xz. And that's it. Okay, fabulous. Now, on this left-hand side, because the partial of z with respect to x is in all 3 terms, I can factor it out. So we've got partial x times xy e to the xyz plus x cosine of xz minus 2yz, and that's equal to negative yz e to the xyz minus z cosine of xz. Excellent. And so now, to solve for the partial of z with respect to x, I'm just going to divide by this. I understand this is undefined. If this is equal to 0, I do not want to have to solve for what's going to make this 0. But as long as when I divide by it, I keep it in the denominator and I don't cancel anything, I'll be able to see from the result that my formula will be undefined at points that make this thing 0. Okay, so partial z, partial x is just going to be a lovely fraction. On top, we've got negative yz e to the xyz minus z cosine of xz, all divided by xy e to the xyz plus x cosine of xz minus 2yz. Again, with the understanding that that's undefined if the denominator is 0. All right, so that was the partial with respect to x. So if I now want to find the partial of z with respect to y, I find it helpful to just write down the new roles that we have. So now we're saying x is playing the role of a constant, y is my independent or my input variable, and z is implicitly some function of x and y. And of course, since x has played the role of a constant, that essentially turns it into a function of y. Okay. All right, so I'm going to take the partial with respect to y of both sides. So partial with respect to y of e to the xyz plus sine of xz minus yz squared equals the partial with respect to y of 5. And again, that right-hand side is nice and simple. That's going to be 0. Just got to write that over here because the left-hand side is going to get kind of long. Okay. I like to put my parentheses around my z just to remind me that's a function, and so anytime I'm taking the derivative of something with a z in it, I'm going to have to use chain rule and get the partial of z with respect to y. All right, so here we're going to get e to the xyz times the derivative of xyz, the partial derivative with respect to y. But again, this is a product because there are y's in that factor, and z was a function of x and y, so there are y's implicitly there. So partial of xy with respect to y is just x times the other factor of z, plus that first factor is xy times the partial of z with respect to y. Okay, so plus, here we're going to have cosine of xz, and then times the partial derivative of x times z. Now again, z is a function of x and y, in particular of y, because that's playing the role of our variable. So this becomes just a constant multiple of z, so we'll have an x times the partial of z with respect to y. If I have a multiple of z, when I take the partial, I'm going to get that same multiple of the partial derivative. Okay. All right, and then minus the yz squared, that's another product because there's a y in the first factor and z was implicitly a function of y. So we're going to have to use product rule, and that means we're going to have to distribute that negative sign after we take the derivative here. Okay. So for the first factor, the partial of y with respect to y is just 1 times z squared plus y times the partial of z squared, that's going to give me 2z from the squaring function, chain rule, times the derivative of the inside part, partial z, partial y. Okay, quick check. We had 3 z's. We have 3 copies of the partial of z with respect to y. So let's just distribute so that we can break the ones in the parentheses out. So we're going to have xz e to the xyz plus xy e to the xyz times the partial of z with respect to y plus x cosine of xz times the partial of z with respect to y. And now we're just distributing that negative. So minus z squared minus 2yz partial z partial y, and that equals 0. Okay, so now here are my 3 terms that involve the partial of z with respect to y. I'll keep those on the left and move everything else over. So we will have xy e to the xyz times the partial of z with respect to y. We will have plus x cosine of xz times the partial of z with respect to y. And we will have minus 2yz times the partial of z with respect to y. That's going to equal what I get if I move the other stuff over. So that's going to give me a negative xz e to the xyz plus a z squared. Now, on the left-hand side, I can factor out that partial of z with respect to y. So that's being multiplied by xy e to the xyz plus x cosine of xz minus 2yz. And it's still equal to that right-hand side. So then if I wanted to solve, and I do, for the partial of z with respect to y, that's going to give me this lovely fraction. On top, I've got the negative xz e to the xyz plus z squared. And on bottom, I've got this mess. So xy e to the xyz plus x cosine of xz minus 2y squared. Again, that's a formula when that's defined, and it won't be if the denominator is 0, but when that's defined, that's going to give me the partial of z with respect to y.